Greetings, AP Chemistry students. In yesterday's lesson, I kind of left you with a little bit of a cliffhanger talking about uh, entropy and enthalpy and how all processes tend to want to be exothermic and increase entropy. And if that happens, a reaction is considered to be favorable. So, first, let's talk about that term favorable. A reaction is said to be thermodynamically favored or favorable if it will occur without any outside influence once you provide the initial activation energy that's required for the reaction to take place. For instance, once you strike a match and you light a candle, that candle will keep on burning. The candle burning is a thermodynamically favorable process. It will keep on happening without any outside influence. Or if you set an ice cube on your kitchen counter, assuming it's above freezing in your house, it will melt on its own. This term was previously termed spontaneous, and you may see that term appear sometimes. The College Board and the AP exam will never use the term spontaneous, and you are discouraged from using that word on a free response question. The term that you should use is favorable or thermodynamically favorable or favored, right? So, what we're going to talk about today is Gibbs free energy, which is represented with the capital letter G. Finally, something that makes sense. So, Gibbs free energy is the energy that's available to do work or the useful energy that can be extracted from a reaction. Because when a reaction occurs, it releases energy, but some of that energy goes into increasing the entropy of the universe. And once energy is converted into increasing entropy, it's completely useless, right? Uh, Increasing entropy is essentially something that happens that essentially wastes the energy. For instance, when you're burning gasoline in your car in order to make it go down the road, that energy is converted into ultimately heat that heats up the surroundings of the car. And that energy, once that energy goes into that form of heat, it's ultimately useless. You can no longer use it. You've created entropy. So the useful energy is the difference between is what's essentially you're able to use. The equation we're going to be using says that the change in Gibbs free energy for a reaction equals the change in enthalpy minus the temperature in kelvins times the change in entropy. Now, just as a side note, Gibbs free energy is named for an American scientist, Josiah Willard Gibbs, who did a lot of work with thermodynamics. And he's somebody who Albert Einstein called the greatest American scientist. Um, the thing about Gibbs free energy is that reactions are spontaneous or thermodynamically favorable if delta G for the reaction is negative. Now, because the way this formula is set up, if delta H is negative and delta S is positive, then the reaction is always thermodynamically favored because our temperature is measured in kelvins, and so that has to be a positive number. So if you have a negative number minus a positive times a positive, you're subtracting a positive here. Negative minus a positive, delta G has to be negative, so the reaction is favorable. If delta H is positive and S is negative, then G will always be positive. But if both values are positive or both values are negative, then whether or not a reaction is thermodynamically favorable depends on the temperature at which the reaction occurs. All right, so let's look at this a little bit more. So we already said that if H is negative, S is positive, G is negative, and the reaction is always favorable because energy and net energy is released from the reaction that's useful. In other words, keep in mind if G is negative, the reaction is favorable. If H is positive, S is negative, G is always positive. If they're both positive, then At low temperatures, and just always envision the lowest possible temperature, absolute zero, even though you would never actually get there. At low temperatures, T is zero, so zero times S is zero. So whatever H is ultimately dominates that. So at low temperatures, G is positive, and then if temperature gets high enough, then your T delta S value will eventually exceed your delta H value, and it will cause delta G to become negative. So it will be negative at high temperatures. And if both values for a reaction are negative, the opposite is true. So if both of these are negative, then that means that the reaction is favorable at low temperatures, but eventually your value of T delta S will become so large, and T delta S would be negative, and you're subtracting a negative, which makes it positive, that eventually at a high enough temperature, this value will cause delta G to become positive at high temperatures. And if we think about the case of ice turning into water, well, the sign for delta H, because to melt ice, delta H is positive. It is an endothermic process. You have to put energy into it to make it melt. Delta S is always positive because we're going from solid to liquid. That's an increase in entropy. You're increasing entropy there. So, what this is saying is that this is not favorable at low temperatures, but it becomes favorable at high temperatures. And specifically, delta G is positive below 273 kelvins or 0 Celsius, and delta G is negative above 273 kelvins. In other words, if you're above the freezing point, then it is favorable for ice to melt, and if you're below the freezing point, it's not. And also, just like with delta H, if you were to reverse a reaction, you would change the sign of delta H, delta S, and delta G. And so if you're talking about water turning into ice, then the favorability becomes the exact opposite of ice turning into water. Those are opposite processes. So at 0 degrees Celsius, delta G is 0. And so what that would mean is that the reaction is not favorable or unfavorable. It's just going to basically stay exactly where it is. However much ice and however much water you've got, that's ultimately what you got. So this is a little overview or summary of that information. Now we will come back to this chart later. So you may have noticed those degree signs with delta H and delta S and delta G. I just want to refresh your memory on what that means. That means standard conditions. If you're a gas, you're at 1 atmosphere of pressure. Solutions have a molarity of 1, and you're in the state of matter that is the most stable at 25 degrees Celsius. Now, sometimes there is a difference between thermodynamic and kinetic control of whether a reaction actually happens. So there are a lot of favorable processes that do not occur at any measurable extent or occur at extremely slow rates, right? So these are said to be under kinetic control. For instance, it is thermodynamically favorable for wood to combine with oxygen and as a result create a fire where it produces carbon dioxide and water vapor. But this wooden desk that I'm sitting at is not on fire right now because it has not been subjected to a high enough temperature to provide the activation energy. Remember, activation energy, that's from kinetics, in order for it to burst into flames. And hopefully that never happens. Um, yeah, so this is typically because of a very high activation energy. Another example, diamonds turning into graphite is a thermodynamically favorable process. In other words, diamonds turning into pencil lead. However, that doesn't happen because the activation energy for that is so extremely high that it never happens. The activation energy barrier is just too great. Diamonds do not just turn back into graphite because the bonds are so strong. To break them and rearrange it would be difficult. One other thing to note, um, just because a reaction is thermodynamically favorable does not necessarily mean that the reaction happens really fast. How fast a reaction happens depends on the rate law and only on the rate law. Rate equals K times the concentration of the things raised to the different powers. Now, I've talked about some thermodynamics. I talked about rate laws. Know what I haven't talked about? Equilibrium. So let's fix that real quick. G and K are related to each other. Delta G equals negative RT times the natural log of K, where we have Gibbs free energy, we have a negative sign, we have the gas constant in joules per mole Kelvin, because ultimately the gas constant is a proportionality constant between how much kinetic energy something has and its temperature. So it relates energy, temperature, all that good stuff. And the value of R that we're using is 8.314 joules per mole Kelvin. So in this formula right here, what this means is that if G is negative, then K would have to be greater than 1 because the natural log of a number greater than 1 is positive. And we have a positive number times our temperature in kelvins, which is positive, times the gas constant, which is positive. So all of this is positive. There's a negative sign in front of it. So G would be negative. If G is positive, K is less than 1. The natural log of a number between 0 and 1 is a negative number. So this would be negative times a positive times a positive times the negative sign makes it positive. And if G is 0, then K would be 1 because the natural log of 1 is 0. Now, I told you we'd be coming back to this chart. I'm adding on to it. So if G is negative, then K is greater than 1. If G is positive, K is less than 1. All right. So then this would be less than 1 at low temp, greater than 1 at high temp, and then the opposite, greater than 1 at high temperatures, less than 1 at low temp. And we will come back to this chart yet another time next week when we talk about standard cell potentials. Now, just a few more things to point out real quick. For delta G, you can do calculations with delta G just like with Hess's law and just like the equation with entropy works exactly the same way. Then you have the equation that relates delta G to delta H and delta S. And it also has the delta G equals negative RT times the ln of K, which also would mean that you could set delta H minus T delta S to negative RT times the ln of K if you wanted to. And we'll learn about this last equation down here next week.